Yeah, completely different topic, ocean biogeochemistry, data assimilation. I want to give a bit of an overview of what we are working with there and what issues are. It's, the abstract sounds much wider than what I can do in 15 minutes, so I picked some examples. What we are doing is basically what we have is a coupled model, so an ocean circulation model, which is then driving the biogeochemical processes model mainly through velocities and temperatures. So the ocean model is giving us the advection of the biogeochemistry, and the temperature is important for the biogeochemistry processes. Yeah, biogeochemical processes models, there's a wide variation of formulations, and this is one example model that we have at our institute. Well, the problem is different from physics. We don't know the equations. So people made up equations for this. And so basically such a processing is we have some nutrients and we have some plankton which is growing using the nutrients. Then the zooplankton is eating the phytoplankton. Some phytoplankton is dying, and then some parts are sinking down. Then there's something in the ground. You have remineralization, and then you go back to the nutrients. So it's some cycling, and this is how the models are built up as source sinks models. And the models, we have a lot of variations. Like, for example, we don't know how many phytoplankton groups we need. There are models with 1. There are models with 100. And there is no agreement on what is really necessary. So could be different groups. We can classify them like by size or by function. So diatoms are kind of clear because diatoms use silicate to build shells. At that point, they are special. But they are diatoms of various sizes. So you can define various diatoms groups. And it's also not completely clear what variables you actually need. Some models only use nitrogen to formulate everything. Zooplankton is similar. You can have different size classes of zooplankton in the nutrients. Some models include iron. Global models typically include iron. Some include phosphate. Depends on the application, not really clear what should be there. Also the intakes that you have, like from rivers or from the atmosphere. For some in the Southern Ocean, iron is quite important. If you're getting close to the coast, nitrogen is important from the fertilizers that go in from the rivers. And then also the light formulation is different. Some or most models just know light, not spectrally dissolved, just photoadaptive available radiation. And others really have spectrally resolved lights. They get more sophisticated, not necessarily better, but more sophisticated. Overall, it ends up that these models have a very high uncertainty. And later in one example, you will also show it. So you can publish a paper with 100% of error in comparing to in situ data, for example. So far higher than what we have in physics. So these are the models. And what we have to directly constrain biogeochemistry is satellite ocean color observations. Like this photo, just taken from the Ocean Color website of NASA Goddard. It's kind of a nice photo. I hope you see this sufficiently. A lot of green filaments. This is the west coast of Africa. Actually, not a photograph. But what it is, these satellites, there are various of these satellites, they measure typically 5 to 8 wavelengths bands in this visible part of the spectrum. Like we see this here, this is one example of such 6 bands which are observed. From this you can do quasi-realistic pictures. But on the other hand, so the satellite data is water-leaving radiance or surface reflectance. And what's then typically done is that we get retrievals, data product derived from these reflectance data. And yeah, the most common product that we have them is a satellite chlorophyll data, total chlorophyll. Chlorophyll is nice because what you see in green is typically chlorophyll, which lets the plants grow. So this is one natural color photo. It's so natural that in the back you don't see anything. But this is a chlorophyll that's derived from it. It's west coast of the US. San Francisco is here. This is what you get. And then, well, a chlorophyll is computed with some algorithm like this, fourth order polynomial of the reflectance at two wavelengths. So you have the ratio of blue light to ratio reflectance at blue, reflectance to green, the log of this, and then you do such a, with some coefficients, fourth order polynomial. You can also combine this with a linear formulation using 3 different wavelengths, but it's all, and this is the important part, it's all empiric. This is fitting toward scatter plots. And then you get such a function, but the scatter plot is wide. It's not a narrow scatter plot. So this is kind of also then implying the data quality is also kind of bad. Already the data quality, the observation error or the measurement error is already high. Yes? In this case, it should, on the one hand, it's upwelling. That means nutrients coming up. And then it's probably also the outflow of the water here that gives you some nutrients. But generally, this is a picture of what you expect, I think, mostly due to the upwellings that we have there. Which actually means that vertical velocity in biogeochemistry is also pretty important. Here we have one example, bit more into the data that we have, like a one-day picture of, this is gridded on a rather coarse grid of from a CVIS satellite sensor, daily 1 day of chlorophyll data, and this is the availability over months, June 2001. The whole month of data from 0 to 27 about, and you see cases like the Pacific, well, sometimes you have 0 data points, sometimes you have 1 data point. Arabian Sea, 0 data points over a whole month. This is what we have to live with. Obviously, we have polar night down here. It's an optical sensor. We don't see anything. Well, there's also not really growth there, but still there's phytoplankton, little bit. They survive over winter. So we have data coverage of 30 to 50%, quite irregular here when it comes to the data. So we have, when we now come to the data assimilation, several issues. On the one hand, on the model skill, we have much higher errors than in physics. Still, the models have some skills. That's good. Otherwise, it wouldn't be possible to do assimilation. Only a fraction of the fields is observed. So basically, we want to constrain all nutrients and all variables in the phytoplankton groups. We have one model I come in a minute to. It's actually that what I have shown. We have 2 phytoplankton groups, each described by 4 variables. We want to constrain basically all from having essentially one type of data. On the observations, well, we have data gaps, so the fields are less constrained. We have rather high data level. It's empiric algorithm, which is basically, well, we put this then also into partly then into representation error. For the assimilation is kind of, at least for chlorophyll, it's known chlorophyll is approximately log normally distributed. So we can do the logarithm of the concentrations and have a normal distribution. We can work with it. I show soon that this is not fully the case. We can have bad problems when we do this. Down the variability we put into the representation error. We only assimilate once per day, sometimes less than that. And representation errors in this case also, well, we don't now, we're expected to be high. Typically, we work with these errors of, say, 30%, meaning 0.3 when it comes to the log data assimilation. And yeah, that leads me to a first example. What I want to show here is assimilation of total chlorophyll in a model with 2 phytoplankton groups. And what we have, the coupled model is in this case the MIT GCM circulation model for the physics. It's a global model, not particularly fine, so 2 degrees, but going up to 0.4 degrees in the Southern Ocean, so with a focus on the Southern Ocean processes. Then this RIKEN model with 2 phytoplankton groups, 4 variables each that describe it. The model is particular in that basically nitrogen and carbon and chlorophyll develop fully independently, fully dynamic independently, which makes it complex, but it's kind of from the processes, it's quite realistic. So we use an ensemble Kalman filter, we use PDAF for the assimilation, and then we just, well, we apply it. What we assimilate in this case is this ESA, Ocean Climate Change Initiative data. In this case, with the global model, we assimilate after each 5th day, so we see some total chlorophyll. Here, a 5-day composite. With the data product, we also get logarithmic observation errors, since also, as we have seen with the processing algorithm, it works also on logarithms. So one has to be a bit careful with the log, but then one can work with it. What's now important is, well, the satellite gives us total chlorophyll, and from the model side, it's the sum of the 2 phytoplankton groups, but then we handle all in logarithmic concentration, so computing the log of all variables of all ensemble states, and then we do basically a multivariate update through the covariances that we get from log total chlorophyll to log single groups. And look into how the phytoplankton groups are influenced. We validate with satellite and in situ data, so colleagues also that produce this data, they go also out with a ship and do a lot of measurements. And so we have the small phytoplankton as a particular satellite data set and of diatoms. So there are other algorithms that try to retrieve single groups which even have higher errors than just total chlorophyll. And so this is something what we use for the verification. So when we now assimilate this, in the back you won't really see units. Well, important is the black is without assimilation, and then we have red and blue quite close to each other, which is forecast and analysis from the data assimilation over 2 years. Here, small phytoplankton is having much smaller errors. You see 0.5, that's log. Diatoms, you see an error of 2, huge error, but still you can validate. You see it's getting better. You see also that the patterns globally are right. So the assimilation overall in this case works, that we can constrain both groups from assimilating total chlorophyll. Also when we compare to in situ data, so it's 1.3, more than 1 order of magnitude error without data assimilation. But that's reduced by the data assimilation. Currently, the alternatives that you can do is basically to assimilate these group data, and then there are actually a few different types, and we are currently working on assimilating group data and seeing how it then also influences total chlorophyll. And in particular, diatoms are much better constrained in that case. What's important, what's interesting here is basically when you the estimated cross correlation. So total chlorophyll is the sum of the 2 chlorophylls. These cross correlations are computed from the logs. And then the red values, well, small phytoplankton here is nicely, well, correlation of 1. But we also have lower correlations, in particular for the diatoms, but also we have negative correlations. So meaning more total chlorophyll, less of one of the groups. And this can be nicely estimated from the ensemble. Second example is now really also toward strongly coupled assimilation, different model. In this case, we are here in Europe. It's a coastal model, North Sea, Baltic Sea. Germany is down here. 5 kilometer nested in. There is a 900-meter model. The physics is running operationally in Germany for example, storm surge forecasting. But we use a pre-operational version, which includes the biogeochemistry model. Looks a bit different than that before. Important is we have oxygen and nitrogen here because it's a coastal model, and we also have oxygen depletion in this case. And the observations we have here now is sea surface temperature, AVHRR. It's a small region, so a bad day and a good day can vary strongly also for the temperature data. Each 12 hours we assimilate. And when we do this, we look here now at the oxygen for on average, May 2012. The free-run assimilation weakly coupled, so we only update physics with surface temperature, and we see, okay, it changes a bit. The difference is is shown here. So it's up to 8% changes, but essentially here in the Baltic Sea, almost nothing in the North Sea, but the Baltic Sea is deeper overall. Then we come to strongly coupled assimilation. Strongly coupled assimilation now means we use a cross correlation between SST and the biogeochemistry. In this case, we look at the oxygen again. The effect is stronger, but it's going in the same direction. I found it a bit surprising that it is like this. The effect is overall stronger. Also, we see more effect in the North Sea. This is now using linear concentration. This is kind of a violation of the biogeochemistry quantities, at least. Chlorophyll, log normally distributed. For the other concentration, we have no idea. We assume also, well, log normal should be a nice model. But this is a bit of a violation, but several studies are doing it. Now we come to using logarithmic concentrations, and then we get this a completely unrealistic field. In particular, here in the deeper part, here also Norwegian Trench is going down to 500 meters. The shallow North Sea looks nicer, but it's really, we get unrealistic cross covariances here between the surface temperature and the subsurface oxygen in particular. So they are kind of this theoretical assumption that we have is kind of not really fulfilled. Well, we have this linear regression between temperature and the biogeochemistry, and we don't fully know what is the right variable to regress with. And seemingly, logarithmic biogeochemistry is not the right one. What we can do here to stabilize is a vertical localization. Then things get better, as we see here, but they are still regional. That's a vertical localization to 10 meters. That's 4 model layers. And still we have problems. So this doesn't solve the vertical localization, does not fully help here and it does not fully solve the problem. Yeah, and with that, I'm running out of time, and I want to summarize just what I discussed. So biogeochemical models, processes, models are mechanistic. Model skill is worse than the physical models. We have ocean color observations. Most direct is the surface reflectance. And then we have the different data products for an empirical algorithm. I've shown the strongly coupled assimilation of sea surface temperature here, which is successful for linear concentration, not for logarithmic concentration. So this log normal assumption might not be fully valid. We have stability issues, and we have to look further into what is really happening here. And one more thing where I want to just quickly show what we do now and next is basically, well, we have radiances at 6 wavelength bands. And this is actually also something which you can assimilate. So this model needed to be, we have adapted it now so that it now is spectral light. And that gives us the possibility to actually directly assimilate all 6 or a limited number of these radiances into the model. And they should be correlated with the biogeochemistry quantities, and I cannot show yet results, so next year I will show results from that data assimilation. Thank you.
Thank you.